Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
Welcome back, everyone. I hope you had an enjoyable morning and lunch. We will resume with talk vision systems and with particular emphasis on low latency vision systems. We will also look at how these application fields are benefiting from FPGA-based implementations. Okay, so the question you might have now is why FPGAs in the first place? And actually, this is not a young question. It has been there for at least 20 years, as I can remember. You might have read an article or two about this question. You might have formed an opinion of yourself, but if you didn't, I will to give you my opinion. So when it comes to vision system, we all know that we have a video stream at the input of the vision system, and that video stream is characterized by a parameter, which is the data rate. Now, the data rate is the product of three factors. It's the frame size, the frame rate, and the pixel size, right? So as far as the frame size is concerned, you can have something from very little, like 320 by 240. This is the typical surveillance camera you have in the parking lot, to something quite large, which is like the 4K or the 8K video that will probably soon become ubiquitous. Same thing happens with the frame rate. You can have any frame rate from a few frames per second to thousands of frames per second, which are typical for some high-end scientific equipment, for instance. Now, if you multiply these numbers, you will observe something, which is the fact that they span a large range, like 4 orders of magnitude. So the data rate can vary quite a bit, from a few megabits per second to gigabits per second. And you have multiple technologies that can absorb this data. You can have CPUs, you can have DSPs, you can have ASICs, GPUs, and FPGAs. Now, if the data rate is small, you can use CPUs and the DSPs. They will do just fine, right? But as soon as you increase your data rate, these solutions will not fit anymore. You are left with the ASICs, GPUs, and FPGAs. Then, if you want to keep your processing pipe, the video processing pipe, flexible, what happens is that you have to drop the ASICs. They have a certain degree of flexibility, but not much. And in the end, you have to drop that solution. You are left with the GPUs and the FPGAs as options. And then, if you also have to keep with the low latency, you are basically left with only one solution, which is the FPGA. Now, why do you need low latency in video? Well, you have a certain type of applications, like the one illustrated in the image, in which basically the doctor requires eye-hand coordination in order to operate the patient. And because he has a video system between him and the patient, the loop has to be kept as short as possible in time. So we have a real-time constraint here. And for such application, low latency is very important. Another application might be in the automotive field, where you have to take decisions very quickly based on what you are seeing, because you need a very short reaction time. But these are not the only reasons why FPGAs do fine in the field of video processing. There are multiple other reasons. Like, one is obsolescence management, and it's very important, okay? It's very important because imagine you have designed a system with an ASIC or a GPU. These are commercial off-the-shelf products. And what happens next is they become obsolete. You will basically have to redesign a whole system, and if you're lucky, maybe only of one board. In that case, you might want to use an FPGA, because even if that FPGA becomes obsolete, you will still be left with the solution of implementing that thing on another FPGA. You might also have a situation in which no chip existing on the market fits your needs. Like you have, I don't know, 13 MIPI inputs and 7 outputs, parallel outputs. So in that case, I guarantee you will not find the right chip that will do that. And you might want to go for FPGAs in this case. Not least, it is much easier to certify an FPGA solution than to certify a commercial off-the-shelf solution, right? So I want to tell you here in parenthesis that at Enclustra we are now developing a range of products that is built to be for function safety. So if you have such concerns, don't hesitate to contact us. Now we will look at certain ways of optimizing our algorithms for low latency. The 2 points that I grayed out here were already discussed by Harry this morning, so I will not touch them anymore. And we will only discuss about how to convert a frame-based algorithm to a stream-based algorithm. You would want to do that if you want to achieve low latency. Then we will look at how we constrain dynamic range. And we will also look at something that is called mathematical rearrangement. All these techniques can be applied to optimize your implementation. So now let's look at how we convert frame-based algorithms to stream-based algorithms. So frame-based algorithms are having basically this structure. They have a camera interface in which you basically convert between a physical signaling that comes from your camera to a byte parallel representing your pixels. Once you have done that, you will want to apply a pre-processing step that can be anything like dilation or contraction, can be a prefilter of some sort, debayering, or even camera lens correction. What you will do next is that you will store that information in the memory just to read it back later on, right? To apply the processing steps that follow. And then you will display the result on the screen. The way you address the memory is really straight. You can address any region. You can apply any computation on that region, store it back in the memory. So from this point of view, this is great. This is basically what a framework like OpenCV, Open Computer Vision, will allow you to do, and you can do great things about that with that. Now, if you go for stream-based processing, things change a bit, and you will not have this freedom of storing your image in the memory anymore. You don't do that because that increases the latency. So you want to keep low latency, to achieve low latency. What you will have, it's a succession of stages which are basically based on the axis stream technology. And in each of these stages, you will process part of your algorithm. So basically you are pipelining the implementation. The signals that you have available to do that are T-ready and T-valid. These are handshaking signals for passing data from one stage to another. You have two signals here that signal the framing of your video, the start of frame, end of line, these kind of things that you have to use in order to apply processing correctly. Finally, you have the T-data, which is the pixel. Or in case you want to parallelize, as Harry said in the morning, you can send 2 pixels at a time, or 4 pixels at a time, or more pixels at a time, and decrease the clock rate probably. Okay, now let's see what happens if you want to apply kernel processing over your image. So this is a small image. The pixels arrive in raster order. And basically, that is the area of interest that you have with orange there. So the pixels entered inside the area, and you want to remember them. So in order to remember them, you will put some flip-flops. Okay, so now you remember the 3 pixels. I'm jumping on the last line, the same thing. And now you want to remember the previous line, and for that, you will not use flip-flops, because if your image is large, you will not use 1,000 of flip-flops to do that. Instead, you will use a block run or another run resource, ultra, and so also from your FPGA. And in order to remember the 3 pixels there, you will again use flip-flops, and again a block run, and more flip-flops, and like that, you have to remember the whole 3x3 array. In this moment, you can apply this to a convolution operator and compute your end result. Obviously, every clock that follows will push that square to the right, and you would have like that the possibility to compute the convolution over the whole image. But this is not the end of the story. There are some details you have to take into account. Like the corners and the borders, you have to deal with them in a special way, because you cannot flush the data as it comes in. So you have to pay special attention to that. And one technique would be to square the whole image with zeros. That is up to you to find a solution for that. Okay, let's look now quickly to how we constrain dynamic range. So in this case, the example is that of a division. You might want to use a division where you want to scale an image, like maybe scale the color, make it less colorful. And in that case, you probably know that a division in an FPGA takes a lot of resources. You have freedom to implement it, like you can make it bit serial, for instance, but then it will take a lot of clocks, and you don't have those clocks to give, okay? Then if you go for a parallel implementation, it will take a lot of area. So it seems like none of this solution is good, but luckily we can transform a division in a multiplication, right? So basically what you have to do is to compute the inverse of B and proceed with the multiplication. But we all know that the 1 over x is not a well-behaved function. It has a huge gradient as you go towards 0, and it becomes almost 0 as you go to large numbers. So basically the 1 over x is varying in a large range, and you would like to constrain that range, and that's the title, constrain dynamic range, to a specific area where you know that the value of 1 over x is well behaving. So in this case, what you're going to do is to shift the b value so that it enters this interval between 0.5 and 1. Then you proceed with the inverse multiplication, and at the end you have to not forget to shift it back, okay? Now let's look at mathematical rearrangement. So this is the formula, the textbook formula for computing the covariance between two images. And if you proceed blindly immediately, you will tell yourself, okay, I need to pass through the image once in order to compute the average. Okay? And then you realize, wait, now I have the average, and I have to pass again through the image in order to compute the differences and to proceed with the multiplication. So what does this mean? It means that you have to store the image in the memory, and this is exactly what you don't want. But if you think for a little bit, you will just realize that developing that formula in a form that is equivalent only means that you have to pass through the image once. Now there is one detail that you have to take into account if you do this, and that is about computation stability, okay? You might have problems with the stability of the computations, and basically anytime you apply numerical computation, you might have those problems of stability. So take care of that if you do this. Now, a more complex example. This is actually the demo that turns in the back. If you didn't see it, it's an edge detector, which is using a 7x7 Sobel filter. We do that by applying a vertical detection and then applying a horizontal detection gradient and then a vertical one, and merging the two by computing the Euclidean distance or the L2 norm if you want. So if you look at this image, you will see that computing the 2D convolution implies 7x7, therefore 49 multipliers. And if you are looking a bit careful, you see that the middle column is only zeros. So you might tell yourself that's only 42 multipliers. But if you are looking more carefully, you will see that the second column is basically the first column multiplied by 4. And the third column is the first column multiplied by 5. So you would say, yeah, I can do 2 vector multiplications. Now, this is just a matrix representation of what was before, right? So I'm going to do a trick, which is putting a convolution sign between the two. What this does is that instead of proceeding with a 2D convolution on the image, you are proceeding with 2 one-dimensional convolutions over the image. So instead of doing it in one step, you will be doing it in 2 steps with vectors that are smaller, right? And by the way, these are the dot products. It's not matrix multiplication anymore. What is important here is that you can change the order. The operation will be the same. The end result on the image will be the same. So this is the implementation that you will do. But mathematically, there is no difference if you put the convolution of the 2 one-dimensional vectors like this or like this. But from an implementation perspective, it makes a whole of a difference. In the first case, you will share flip-flops. And in this case, you will share block routes between the 2 branches. And this is very important because this is conserving very, very expensive resources, right? So you want to save expensive resources, which are the block routes. So you basically will prefer this implementation to the first one. Okay, so now let's look at exploiting the redundancy. When you implement the multiplication, we know one of these vectors. You might probably notice that some of the coefficients that you have are just the same with opposite signs. So -1 and 1. Four and -4, they are symmetrical, and 5 and -5. What you can do in this case is use an additioner to do exactly the same thing. You might even go further with the observations by saying that, okay, multiplication by 0, it's basically 0. Multiplication by 1, it's just a y, right? Multiplication by 4, it's again just a wire. You just have to shift 2 bits. And multiplication by 5, basically it's 1 and 4, and you add 2, and basically you have a multiplication by 5. So that's what you get. In the end, you have started with 49 multipliers, and you ended up with 0 multipliers. So just a bit of thinking got you there. So just to resume, we have seen a few implementations. The naive one, which uses 42 multipliers. We remove the 0 column, so it's only 42 times 2 for the two matrices. Then we have a LUT optimized one, which only uses 14, and the DSP optimized, which we have seen uses 0. And then we tried something, namely put this algorithm through the HLS developer. And we observed that he came up with 0, which is very good to know. I mean, he's doing quite a good job. It is doing quite a good job. Only the number of LUTs is large. But this is not to say that HLS is not good. It is good for the purpose. If you want to go fast to the market or you want to try your implementation, just go over to HLS. So what happens if you have a complex video system that you have implemented and you want to bring it up? So the first day of the bring up, you switch on the camera and you have a black screen. So I don't know how many of you would expect something else from such a complex system, but this is usually what happens. So why does this happen? Well, basically because you have quite a number of new developments that you have done. You have new hardware, you have new processing in the video pipe that you wrote for the first time, and you have glued all these things together for the first time. And then you have also the drivers for those parts that you wrote in the FPGA, and the test application that drives the screen. It's also new. You also have a number of things that you have used for the first time. And those are the camera, the third-party receiver, and the third-party transmitter. Also the display, you used it for the first time, the drivers for the receiver and transmitter. So, second day of bring-up, you put all the team together and you ask them, why is this thing not working? So the first person you ask would be the application software team, highest level. And they tell you, well, don't ask me why this is not working. We don't get any data from the FPGA. So you go to the Linux expert and you ask him, is your driver not working? What's happening? Well, actually, we don't get the data from the FPGA, right? So next thing that you will do is that you will go to see what is happening at the level of the IP. The thing is that the FPGA team has simulated well the behavior of the FPGA, and they are very confident about it. So the problem is not there. You contact the camera vendor and you ask him what about the configuration of your camera and so on and so forth. And everything turns out to be correct. So the problem is not there either. In the end, you end up talking with the system architect, the system engineer. And basically he says, okay, let me talk to the hardware guy. This is the last guy which we didn't talk to. Okay, so we talk to the hardware guy. And they tell you, there is something we forgot to tell you. Actually, we changed the polarity of the LVDS line with the camera in the last moment. Sorry for that. So this is not to say that the problem is in the hardware all the time. Far from that. The idea here is that with such a complex system, the problem can be anywhere. And this is a typical needle in the haystack problem, right? you are starting to look for the problem in a large space of possibilities. It is code-wise complex because there is a lot of code that you have to look at, to search in, and it's also data-wise complex because you have to look at a lot of data to track the bug. Just imagine that the FPGA guys, when they implement an FPGA IP, they cannot simulate even a frame of video. It is impossible. It takes too much time in simulation. So basically, they look at a corner of an image or something like that. So what can you do? Well, you can keep the needle count small. What does that even mean? Well, for me, it means that you might want to apply a quality management system to your development. The definition of a quality management system is just that it tries to minimize the systematic errors that you bring in a process of design, right? And that means exactly that. So apply a quality management system if you don't already have one. Yes, you can have a clean design process. That means that you might be willing to think before coding, think about the behavior of your design, about the data rate, about the burst behavior, do you have peaks of data, and so on and so forth. Think about all that. Power consumption might be a problem at some point, and so on and so on. All the details you can think of. Also, all the time, do unit testing of software, of firmware, have test benches. Don't leave any piece of code uncontrolled, right? You don't want to put many things that don't work together and test them together. You might also want to do continuous integration and automated builds. And that also means that you will not provide a bit stream that is 1 week old to your team, to the next in your team, right? You will always provide the bit streams that are the latest. Use existing code, either your code or something that you buy from a third party, because those pieces of code are non-working, right? Also, you might want to hire top-notch developers. Now, this might be a bit controversial, but what it means that young developers will produce more errors. And then if you need all the people, like 10, 20 people, to sit in a room to search for an error in the code that was produced by a junior developer, that will cost you a lot of money. And if you have a senior developer, the number of errors produced might be less, and you are not exposed to such situations. Yeah. Slower is faster. So this is an advice for project managers. Don't push your engineers around. Don't push them to give results quickly. Let them simulate the things, because they will do what you tell them. And then you will have that room full of people. So divide the haystack, okay? This is a broad assertion designed for bring up, but let's see how this can be done. So build in your hardware diagnostics. If it's software, put some pre-tests, right? If it's FPGA, put some flags there that will mark unexpected situations, unexpected conditions. Some malformat of the data stream, malformatting of the data stream, or the fact that data rate with the DDR memory was exceeded, or something like that. You might want to break the processing chain. So this is something that I will illustrate on the next slide in more detail. And you might also want to implement parts of your design in standalone test benches, right? To test the receiver, to test the transmitter in a separate manner. So what does it mean to put flags? Well, you can implement a flag in the processing B IP core so that you flag an unexpected condition, as I said. Or you can put checkers at the output of each IP in the processing chain. You can also put a test generator a pattern test generator at the input of each module. This will help you a lot to isolate problems. You can isolate every IP in the processing chain and test it independently. This is very important. In order to do that, you will also need to write some pieces of code that are for each of those segments. So in this kind of setup, you can imagine that if you have a problem in the processing chain, there are 3 segments, and you can have 3 teams working in parallel in locating the problem on the processing chain. Okay, and now we will pass to the second part of this presentation, which is the AI in FPGAs. We will look at where FPGAs make sense for AI, and also what are the implementation options that we have with FPGAs in terms of AI. There are 2, DPU-based AI inference and unrolled AI. So let me give you a brief refresh of the terms used in AI. So under the umbrella of AI, you have several things. You have natural language processing, you have expert systems, and you also have machine learning. This is of interest for us because it encapsulates the part which is deep learning. These are algorithms that are training your neural networks. In this case, we will be looking at deep neural networks that can be of several types. You have the multi-layer perceptron. You have the recurrent neural networks. The recurrent neural networks allow you to detect movement on an image. For instance, you can have a ball going to the left or a ball going to the right. You can detect that. You have some memory of the previous range in that kind of things. And you have the convolutional neural networks, which are of interest for us today. So we are basically using convolutional neural networks for implementing vision. Now everyone knows that there are 2 parts in AI. One is learning, training of the neural network, and the second is inference. When it comes to learning, I think there is global consensus that FPGAs are not ideal. We will basically use GPUs or certain ASICs to do that. It's just computation and computation again computation till you get the convergence and the parameters for your neural network. And as far as inference is concerned, FPGAs can help with that. So when does FPGA make sense for AI? And this is an image you have probably seen multiple times, right? This is the image that compares dedicated silicon with FPGAs. I've seen this at 20 years ago.
Yes.
It's the same image. At the very beginning, FPGA make more sense because they have lower front-up cost, right? And they do have higher per unit cost, of course. And there is a point where the volume of producing these elements will put the dedicated silicon in front as a solution because they have lower per unit cost. So this is the image. Now, when you are looking for performance, when you are looking to train a neural network for performance, what happens naturally is that you program that neural network and you specialize it. And by specializing it, you will push the number of components to a low volume. What does that mean? It means that there will be less and less people interested about that specialization, right? The customer base is going to be smaller and smaller as you specialize the thing. This has as ultimate result the fact that the FPGA will be always referred to dedicated silicon as soon as you specialize it, right? So you will be within this window of opportunity, and when you are there, you basically have the two solutions that we mentioned. You can go for the DPU-based implementation, which is well supported by the Xilinx VTIS AI environment, or you can go for unrolled implementation, which is not supported in the standard workflow of Xilinx, but you have a tool which helps you do that. It's called Thin. So let's look a bit what DPU-based implementation is all about. A DPU is a deep learning processing unit. It's a soft IP. It is a coprocessor. It is something that you take and put in the FPGA. And you also need the support from the CPU in order to operate it. It cannot work standalone, okay? So the CPU will put the data, the image next to your DPU, will put the feature map parameters to the DPU, and by the end of each operation, each iteration, it will do this again and again. So the DPU is a soft IP, as I said, and you can download it to integrate it with Vivado. It is not integrated by default, so you have to download it to integrate it. It comes in several instances. You can have smaller versions of this IP or larger versions of this IP. Of course, if you go for largest versions, you will lose a lot more resources. So you have to target the size of this DPU according to your needs. This is a typical processing chain for the DPU. Basically, you will have a framework, a standard framework like PyTorch or TensorFlow at the very input, and then you will have the usual steps of quantization, parsing, and compiling, just to produce the runtime binaries that you deploy on the FPGA. So all this workflow is taken care by the VTIS AI workflow, and you are not alone by doing that. You have also a lot of application notes and information available. If you go for unrolled AI, you are on a relatively uncharted territory, okay? And there is Versal. Versal is somewhere in between the two. It gives you some hard IPs that optimize the performance. So when it comes to performance and specialization, Versal AI pushes the boundaries a bit more, okay? So here is some information about him. You basically compile the output of the framework, which is PyTorch or TensorFlow, and then basically you will generate HLS code that will be taken over by Vivado later on in the process. Some information about Fin. There are two links there that you might want to look at. They are useful to learn about how to use it. So what are the advantages and disadvantages of unrolled AI? First of all, they are extremely resource efficient. They are tailored for your application. There is no resource there that is unused. Everything is for the purpose of being used. They are extremely low latency, and they have a high throughput rate. The inference rate is that of the clock. So that is a good reason to go for unrolled AI. This is a constraint for your application. In terms of these disadvantages, basically you will require very aggressive pruning and quantization in order to achieve a neural network which is small enough to fit in an FPGA. If you don't do that, you will have a neural network so large that it will not fit in the FPGA in the first place. And definitely going for this thing requires a lot more effort. So if you go for DPU, you will have higher bit precision, you will have lower effort to achieve your goal, and if it works for your needs, go for the DPU. Okay. If you go for the on-road execution, you will have a higher inference rate, but as soon as you don't need it, don't go for it. It also has an extremely low area, extremely low latency, and power. Okay, so what do we offer in order to support you? So Enclustra will give you some application notes that you can download from the GitHub. In those application notes, you can read how to use HDMI, MIPI, VPUs, and the GPUs, and the DisplayPort. It basically teaches you whatever you need to know. We also have design kits that are ready to be used immediately. They are, when you open them, they are already running an application. You can also download the reference designs, of course. And of course, we have the whole spectrum of design services that you might need. Software, we can offer you design services in the firmware and FPGA as well, in hardware as well. Should you have a project of your own, you require consulting, that's also something we do.
Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.